Okay, in this chapter we're going to start looking at algorithms, and algorithms are what we use to solve problems, perform calculations. So here's a nice simple definition of an algorithm similar to the one in your textbook. An algorithm is a finite set of specific, detailed steps that can solve a problem or perform a calculation. The most important parts of this definition are the fact that the algorithm is finite, meaning that it will eventually finish. There's no use having an algorithm that will never actually finish running, and that the set of steps are specific and detailed so that there's no ambiguity in them and everybody would follow them exactly the same way. We perform algorithms all the time, like tying our shoes or driving a car or all sorts of other things. We already know a set of steps to follow to perform something, but actually articulating it and writing it into code can be a bit of a challenge. But if you're a computer science major, then you'll be spending a lot of time first designing algorithms on paper and then trying to implement those into a specific programming language. Here's an example of an algorithm that we'll look at this semester. Searching for a number in a list. Here's a list of numbers. Now this list is unordered. It's just a bunch of numbers. They're all distinct, meaning we don't have the same number repeated twice. But obviously if I asked you to determine whether or not there was a number in this list, you could probably look at it and tell me. But what we need to do is think about how a computer algorithm would do this. A computer can't look at the whole list and just say, I see it. It has to have a series of steps it can follow. And the basic idea is you're going to start working your way through the list. Is it this number? Is it the second number? Is it the third number? Is it the fourth number? And you're going to keep going until either you find the number you're looking for or you run out of things in the list to look for, and that means you didn't find it. Okay? So this is the pseudocode from our textbook. It's a procedure linear search. We call this pseudocode. It's not a programming language because this is not exact syntax of any specific language, and rather than write it in a specific language where you might or might not be familiar with, this is what we call pseudocode. It looks like computer code, but it's not exactly computer code. It's very similar to an old language, Pascal, which makes it easy to read. But basically, we just want to learn how to follow this algorithm and trace it on paper. And then if you have to program this, you would do that in a programming class later. So we have a procedure. The procedure is the algorithm itself. It's got a name, linear search. And the parentheses here show us that we have some inputs into this linear search. If you're going to search for something, you're going to have a number x that you're searching for. We're just going to make sure it's an integer in this case. And we have to have a list of numbers that we're looking through. So A1 through AN represent the list. Up here, this would represent the list A1 through AN, and X is the number that you'd be looking for. Okay? So the way the algorithm works, again, is you say, is it the first one, is it the second, is it the third, and so on. So we start with a counter variable I. I becomes 1, so that we start at the beginning of the list. And what we're going to do is use this control structure in which most programming languages have, called a while statement. A while statement says, as long as the conditions inside the while statement are met, keep performing the step inside the while loop. What we're going to do is, as long as I is less than or equal to n, that means you haven't reached the end of the list, right? Because n is how many items there are in the list. As long as you haven't reached the end of the list, and x is not equal to a sub I. A sub I is the current one in the list you're looking at. If I was 3, you'd be comparing to A3. As long as you haven't reached the end of the list and you haven't found the thing you're looking for, go to the next one. I gets I plus 1, increases the index counter variable to go to the next one in the list. Now, this loop will continue until one of these two conditions is false, and remains true as long as both pieces are true. Now, when the while loop finishes, we still have to figure out which one of these two conditions caused the while loop to exit. If the first condition becomes false, if I is no longer less than or equal to n, what that means is I is now greater than n, and that means that we move beyond the end of the list. Now, if we've moved beyond the end of the list, and that's why we stopped, then that means we didn't find it. If we stopped because x equals a sub I, if this becomes false, then x would actually equal a sub I, and that means we actually found it. Okay? So the way we're going to do this here is at the end, after you've exited this loop, if I is less than or equal to n, meaning I is somewhere within the list, then you found it, and the location of the x that you're looking for must be at position I. Otherwise, that's what else means, location gets 0. So if we don't find it in the list, we return the number 0, and then the person running the program knows that it wasn't found. Okay? So here's how we're going to trace the linear search algorithm to look for the number 12 in the list over here. Okay? So we have the same list of numbers. We're going to look for the number 12. What we might want to do is start off by labeling x equals 12, and then we're going to label these out: a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, a sub 8, and a sub 9. Okay, and make it easier to sort of search through this list. Now, as we go to perform this algorithm, right, we have the I variable that we're going to have to keep track of. Okay, so I starts off as 1. Right, this is what we've got to write down on paper to show that we're following the algorithm. Okay, the while statement includes 2 conditions. So is 1 less than or equal to 9, since in our case n is 9, we have 9 numbers in this list. The answer to that is yes. You could use a y or a t for true. Is x, 12, not equal to a sub I, not the 1 itself, I is 1, right? But a sub 1 is 4. 12 is not equal to 4. That is also true. Okay. So since both conditions are true, what happens? I gets incremented to 2. And then we say, is 2 less than or equal to 9? That is true. Is 12 not equal to 7? Right? Because now a sub 2 is 7. That is also true. So I gets 3. 3 less than or equal to 9. True. 12 is not equal to 2. That's also true. I equals 4. 4 is less than or equal to 9. That's true. 12 is not equal to 1. That's true. I equals 5. 5 is less than or equal to 9. Hopefully you can see what's going on here. We're basically working our way through the list, incrementing as we need to. When we get to I equals 7, 7 is less than or equal to 9. That's true. 12 not equal to 12. That becomes false. Okay? So we're no longer going to increment I. We're going to exit the loop, and we're going to be at our if statement. Now we have one more condition to check. Is 7 less than or equal to 9? The answer is true. So we're going to set location equal to 7. Okay? And what that means is that the number 12 is sitting in position 7, and you can see that right here, that the number 12 is in position A7. So that means we found the list, the item in the list. Okay? Then we're going to look at one more example where we don't find the item in the list. The tracing of that is going to take a little bit of time. So I think we'll do that in the next video.